In previous courses, we were used to having functions that accepted a single number as input and gave a single number as output. Typically, we would plot the inputs on a horizontal line, the outputs on a vertical line, and get our familiar y equals f of x picture. More recently, we've been looking at vector-valued functions, which are somewhat similar, except they take numbers as inputs and produce vectors as outputs. In this video, we're going to begin looking at the next case that will be of interest to us. This is when you have several independent variables, but the function value is a real number instead. Let's look at f of x equals x squared plus 3. This is something familiar to us from Calc 1. More recently, we've had vector-valued functions, but now the kind of thing we're going to look like is x and y go in as inputs, and a number, in this case x squared minus y squared, comes out as output. It's important to understand that x and y are completely independent of each other now. I can pick various x values, but keep the y value equal to 1 and calculate x squared minus y squared. In Calc 1, having a bunch of y numbers the same would be no problem, but having a bunch of x numbers the same would be a problem. If this were Calculus 1 and y were a function of x, this second table would be no good. Unless otherwise stated, the domain of a function is the collection of all inputs for which you can get a function value. The range is the collection of all function values. In our new setting, the domain is going to be a subset of the two-dimensional plane, and the range is going to be a set of numbers. Looking at f of x and y equals x squared minus y squared, obviously I can square any two numbers and then subtract two numbers. The domain of this function is the entire xy plane. Usually determining the range is harder, but in this particular case it's easy. If x and y were both 0, the function value would be 0. If I only think of points that are on the x-axis, the y-coordinate would be 0. My function value would just be the square of the x-coordinate. I can make that number equal to any positive number that I feel like. For example, if I wanted to get function value equal to 1 million, I could just set x to 1,000. On the other hand, I could look at points that are on the y-axis. The function value would be the negative of y squared. I can manufacture any negative number I feel like from that. For example, if I wanted the function value to be negative 1 million, I would just make y equal to 1,000. I can get positive things, I can get negative things, and I can get 0 for an answer. This line of reasoning tells me that the range of this function is the set of all real numbers. In Calculus 1, the graph of a function was the graph of the equation y equal f of x. In our new setting, we're going to need both x and y to serve as inputs, but in three-dimensional space, we can draw a third coordinate axis at right angles to the two that we have to start with. The graph of a function, f of x and y, then, will be the graph of the equation z equals f of x and y, which you'll recall typically is some sort of surface in three-dimensional space. plus y squared plus 1. The graph of that equation is z equals x squared plus y squared plus 1. Recalling our discussion of the quadric surfaces, this is an upward opening parabolic bowl that has been shifted upwards 1 unit in the positive z direction. I'm plotting for x's between negative 10 and positive 10, the same for y, and as you can see, I get my upward opening shape just as I thought I would. Okay, equals 1 over x squared minus y squared minus 4 is obviously going to have trouble. If the bottom of the fraction is 0, then this doesn't make any sense. The bad spots, the places where this is not going to behave well, is a hyperbola in the plane. If the number on the bottom was close to 0, but positive, you'll get large positive function values. On the other hand, if the number on the bottom is negative and close to 0, you'll get negative function values which have large absolute value. Picture a little bit more understandable. The colors indicate the function values. As you can see, there's some problems along that hyperbola, but you don't really get a feel for how bad it is until you look at it sideways. There are blue points close to that hyperbola, large negative function values. There are yellow points on the hyperbola, or close to the hyperbola, indicating larger positive function values. I had to adjust the z range to get a reasonable looking picture. This function acts mostly very nice, except on that hyperbola. As long as you stay away from the hyperbola, this is a perfectly nice function. Graph of f of x and y equals the square of the fraction x squared minus y squared over x squared plus y squared. This function obviously makes sense every place except the origin, where x and y are both 0. This doesn't seem like that bad of a function. It's sort of quadratic upstairs, quadratic downstairs, and then the square of that. But it turns out that this is actually a very bad function. I already see a very complicated behavior. It looks like there are straight lines that I can travel towards the origin on, where the function appears to more or less keep a constant value. The true weirdness of this graph is not apparent until you turn it and look at it from other angles, though. This is a very weird function. Nothing like this ever happened in Calculus 1 or Calculus 2. We are in new territory here. We're in the land of functions of several independent variables, and as you can see, looking at this picture, weird things can happen. All I wanted to do today in this video was to give you a very quick introduction to the idea of a function of more than one independent variable. The next thing we're going to do is think about limits and continuity. Once we know that, we can talk about derivatives, and we will be back in the calculus game again. I hope everybody has a good day. I'll talk to you again soon.